Hello, we are Team Axe. Our group members are Andrew Williams, Xander Sahin, and Evan Burke. Here is the agenda that we will be covering during this video. GRU has tasked us to build a machine that can deploy, clear the heat-seeking missiles, retrieve the children, shrink the moon, and return the moon to orbit to save his children and defeat his rival, Vector. As can be seen, the most important customer requirements are autonomous operation and maximizing points scored. Autonomous operations required per competition requirements to score any points, and maximizing points scored ensures that Vector is defeated and that a robot beats the opposing teams in the competition. The most noteworthy synergy was between the percent chance for mechanical failure and maximizing points scored. However, the biggest drawback is between the percent chance of mechanical failure and the bill of materials budget. The probability for mechanical failure determined through testing shall be less than or equal to 1% to ensure optimal performance in the competition. At least 75% of possible points shall be acquired consistently at a minimum. Placing a shrink ray in the exosphere is a very important specification, as 44 points can be scored and receive the 4x multiplier for double egress. This is more likely to be scored than placing the moon in Zone 1, which rewards 50 points. The most important subfunction shown is deploy robot, as no other subfunctions can be performed unless the robot deploys. Also, egressing the centerpiece plane and egressing the start zone are extremely important subfunctions, as they allow us to get the 4x multiplier for moon placing and shrink ray scoring. Our method of accepting the shrink ray changed with the CHAD design, as we loaded the shrink ray sideways as opposed to loading it in a tube per our morph chart. One major difference with the CHAD design is the way that we accepted the moon. Instead of using a C-grip, we used a box to hold the moon in place.
Our design objectives were to design a machine that can consistently perform the tasks set forth by GRU. We also want to make sure that our machine is innovative and looks nice. This consistency is achieved through good manufacturing practices such as high precision machining, i.e. laser cutting, and overall testing and perfecting of our subsystems.
One of the most unique and central components of our robot is our drivetrain mechanism. As you can see, we have a mess of gears and pulleys going all the way down from the large motor to the wheels. And from the motor to the wheels, we have a 1:8 gear ratio. The reason we drive this slow is so that we can save some torque for our pulley. So actually, as we're driving onto the field, we're simultaneously lifting the pulley, which is preparing us for scoring the moon, while also lifting several strings, which eventually pull out dowel pins and release the flipper mechanism.
A unique feature of the CHAD design is its method of clearing the missiles. Unlike most teams, which clear the front missile and then the two back missiles separately, CHAD clears all three missiles simultaneously, providing a simpler operation. It's all performed passively, and it has had a 100% success rate over the last 10 trials in clearing all of the missiles. The front two flippers actuate outward, and the back flipper actuates across the bottom of the robot, such that none of the missiles are knocked out of the arena.
Once we approach the centerpiece and our beacon hits the long arm limit switch, it sends a signal to our solenoids, which fires the shrink ray and anti-shrink ray arms respectively. Moving to the moon arm, one major advantage of our design is that the placement of our moon arm pivot allows for a short rigid arm that can force the moon down onto the centerpiece, which can be demonstrated here. Once the moon is placed, the arm is able to quickly pivot backwards, and then the drivetrain backs us up slightly for the double egression bonus. Moving on to some of our alternative designs. The mobile cart design is mostly the same as CHAD, the few key differences being the lack of a side support and the usage of a drawer slide to center the flipper pegs. It offers similar advantages and disadvantages, those being able to move to the centerpiece for scoring, but it could also have trouble with the scoring position consistency since it's a cart. The angled drawer slides design features an upward angled drawer slide powered by a winch. It also has an active claw gripper that can easily grip and release the moon. Some strengths of the design are that the base doesn't need to move in order to score, while a major drawback is that it has a smaller window for scoring. The steep telescoping arm design features an upwards telescoping arm and a tank drivetrain that is released with a brake at the end, which sends it down a ramp. Some strengths are similar to the angled drawer slides in that the base doesn't need to move in order to score, while some weaknesses are that it's not nearly as reliable for aggression or arm extension. As you can see in our first level evaluation matrix, the angled drawer slides design is shown as a datum because we figured it would perform decently well in each of the tasks. The mobile cart design and CHAD score fairly similarly because they're based off of each other, and the steep telescoping arm design is behind by quite a bit. Moving on to the third level evaluation matrix, CHAD moves a bit ahead of the mobile cart due to the fact that it is more aesthetically pleasing, easier to set up, and more serviceable.
Our team definitely used the earlier class competitions as a testing ground for iterating and prototyping our final design, the CHAD. Going into the final competition, we were seeded 36th out of 48 teams, although we performed incredibly well, scoring an average of 276 points and never scoring below 204. Our moon placement mechanism was incredibly accurate, with all but one round placing in zone 2, and on the other hand, our shrink ray placement was not nearly as accurate. Although we made a last-minute change, which was successful to launching them sideways onto the centerpiece, our switch holder was too low, and we would have discovered this had we had done more track testing leading up to the final competition. Our team was honored to have been recognized as first in design review, acknowledging our innovative design and the effort that we put into the aesthetic and the outward view of our robot. As well, we developed more consistency throughout the competition and placed first among all 48 teams in the final competition. I think the greatest takeaway that our team discovered throughout this competition was that we need to test more. Although our thoughtful design made it so that our track time was less important, we definitely needed and could have benefited from having more time on the track. Looking back on this class, some of the biggest things that we have learned is that testing is incredibly important, and having consistency is more important than maximizing points. While there are certain things that you don't want to reinvent and certain mechanisms that work, I think it's important to still think outside the box and not go with a traditional design just because other teams have found success in the past. In general, it's best to think less and prototype early in the beginning and leave the thoughtful CAD for the final design, where you can expect to remanufacture and build a final robot to perform well.